Welcome to our channel where we talk about the core knowledge needed in various specialization within the field of traffic operations. Majority of the content in this video is written by Professor Jiangling Wu. My name is Amit Kumar Singh. I am a licensed engineer in the state of Texas. I received my bachelor's degree from IIT Bombay in India and my master's degree from UT Austin. Other contributors of this work include Prensu Singh, an artificial intelligence engineer, Nidhi Kumari, a computer science engineer, and Namrata Kumari, a data science engineer. Now let's get to the main content of this video. In previous video, we looked at the traditional approach to do descriptive safety analysis, which is Excel based formula, and we kind of looked into the dashboard advantages of using dashboard instead of using Excel based formulas for safety analysis. In this video we will look at some basic crash dashboards, and then we can also look at some advanced things we can do with dashboard. So let's call it advanced descriptive analysis. That's given in 4.1.6 in the PDF. We have a dashboard here. We can see the total number of crashes are here in this orange panel. Then there we have KAB crashes, intersection related crashes, crash severity, manner of collision. Like I mentioned in previous video, if we click on any of the charts, so let's say I'm clicking on the red rear end crashes, then all the graphs and everything will filter out for rear end crashes. So it's an interactive and intuitive way to work with Power BI. Let's say I'm interested in KA crashes, so I'll hit control on my keyboard and select KA. So we'll not look into how to build this Power BI dashboards. How to use them is very easy. Even a high school kid can learn it in a week or two. It's not that big deal, but the important point is what kind of analysis we do as a part of this crash analysis is important. So typically we look at intersection related crashes, severe crashes. It can be KA crashes, it can be KAB crashes, or it can be KABC crashes depending on the study. Here we have total crashes. Let's say we want to focus only on pedestrian crashes, so we'll click pedestrian here and we'll filter out pedestrian crashes. Now the study has changed to pedestrian study. Let's say we are interested in pedestrian and motorcycle studies, motorcycle crashes. So pedestrian and ped cyclist is the motorcycle here. So pedestrian and ped cyclist is bike and ped crashes. So these are bike and ped crashes for our study area. So this is how a dashboard can easily help us to perform the crash analysis intuitively and faster with good presentation. The next one, we can look at the persons factor. So I have person factor on different tab. We can look the crashes by driver's age, gender, severity. We can choose whether the person needs to be driver. So let's say we click on driver, then these are different distribution of percentages for different attributes. Alcohol related crashes, seat belt uses. The seat belt uses is something many state DOTs are interested in to see within crashes how many crashes were there when there was drivers were not wearing the seat belt or passengers were not wearing the seat belt. Similarly, we can do a lot of analysis with vehicle crashes. So here I have crash contributing factor. For this particular example, there are a lot of pedestrian related crashes, and then vehicle category here is car only. So the filters are connected. So if I remove the filter from here, then I'll go back to persons data. The filter, this is total crashes because I have removed the filter from the first page. So this is the total distribution of all the crashes. So if I go to vehicle, I'll notice unsafe maneuver and speeding is leading cause of crashes in this area. And these are different vehicle categories. Passenger cars accounted for 84% of crashes, and these are travel directions within the study area. So Dashboards are very intuitive and faster and simpler and better way of performing crash analysis, and it has several advantages. So we typically use our dashboards over Excel's um, for our analysis. So there are some benefits that are mentioned in previous video. Dashboards can be put online. Dashboard does not have data limitations, so we can load the entire state worth of data. We can add all the attributes. In Excel we typically only add let's say let's say like 5 to 10 attributes, but in the dashboards we can load more than 100 attributes and try to see the trend in all the attributes. So it's more detailed than Excel analysis, and there are many advantages to it. So on this screen I'm only showing 3, but there can be more than 20 different charts showing 20 different things. Now we will discuss how we can take the simple dashboard and do some advanced safety analysis with those dashboards. So uh, section 1 4.1.4 advanced descriptive analysis. I think last time I said 4.1.6, so it's 4.1.4 where we are discussing some concepts related to advanced descriptive safety analysis. So traditional crash analysis has following elements. First we figure out the crash rates. So compare the corridor or roadway crash rate against the statewide crash rates. So that's the important point to remember, is in traditional analysis we figure out the severity or necessity of safety analysis based on how corridor is performing as compared to the statewide data. So statewide data kind of sets an expectation on what to expect, and then we compare the roadway or corridor data to see whether we are whether the crashes are more severe than expected. Now the second thing is we look at the distribution of crashes. That is, I will explain this one through the table which is available on the next page, and then percentage distribution of crash contributing factor. Then the third thing we do is we look at the crash contributing factor and see what are the different crash contributing factors and what are the percentage distribution of them. Usually speeding is usually the highest. Speeding, then we have unsafe maneuver is usually there, and then many others crash contributing factors categories. So by looking at these crash contributing factors and percentage distribution of them, we can figure out what are the potential reasons of crashes. So we will focus on the point number 2 and use point number 1 to bring some solutions to point number 2. So we'll focus on point number 2 first, and then we will look at how point number 1 can help with point number 2. So here is a table. We can create hundreds of tables like this using dashboards. So let's say this table is created using a dashboard. Here we have crash severity, intersection related attributes, alcohol related, manner of collisions, weather related. We can have hundreds of tables like this in dashboards, because dashboard does not have a data limitations or processing limitations, and once we set the dashboard for one project, we can keep using it for multiple projects. So what we have here is hundreds of tables like this. Now if we are trying to make sense of this table, and let's say we are looking at manner of collision. Here we can see the sideswipe crashes is 40%. Now traditionally what we have done is we have looked at this 40%. We looked at different attributes in different tables and try to find the one which stands out. So we looked at the side swipe crashes, and let's say it's 40%, along with the left turn crashes, which is 30%, which is very high. So by looking at these numbers, we can say roadway has side swipe crashes or left turn crashes. However, the percentage distribution does not tell us whether this 40% was expected or not. It may happen that for the similar facility, the side swipe crashes typically are let me change the color. So typically, let's say for a similar facility, the side swipe crashes are 60% and left turn crashes are let's say 10%. So in this case, actually the side swipe crashes are better than expected and left turn crashes are worse than expected. So this is an example where the percentage distribution can tell us some things but not everything. It can tell us there are more side swipe crashes, but it does not tell us whether we should be expecting that number or not. So that's a big limitation of traditional approaches of safety analysis. Is no matter how many dashboards we are building, we need to compare it with something to figure out whether those numbers are um, those numbers make sense or not. So that's an important limitation, and we will try to tackle this limitation under advanced descriptive analysis using this point number 1. So we'll use the tool which comes from point number 1, or logic which comes from point number 1, to solve this problem of what to make sense of this number. This is 79.6. Is it a high number or is it a low number? Let's say alcohol related crashes are 1%. We don't know. We don't know whether this is good or bad, or what to expect. So to set the expectations, what we do is we can, with the dashboard, we have the statewide data. Then we can bring the chart tables in from the similar facilities, and then we can compare them to see whether some numbers are high or low. So the next what we will do is we will look into the concept of similar facilities. So this one, what we do is compare the roadway crash rate against statewide crash rate for similar facilities. So first we will look at how to define the similar facility for different projects, and the concept of similar facility will change based on the attributes as well. Here we have, with the development of big data analytics using dashboard, it is possible to compare percentage distribution for each crash type in an attribute against the percentage distribution of other crashes under similar conditions or similar facility. Similar conditions here is the similar facility. The similar condition for different attributes are different. That's a very important point to remember, is we are not just gonna build a table of the statewide and try to compare. So we need to figure out, when we are building these tables for the statewide, whether we are including rural or urban area. First one, we need to build this dashboard by rural or urban. Then we need to figure out what kind of roadway we are comparing, whether we are comparing interstate, IH, whether we are comparing state highways, whether we are comparing farm to market road, whether we are comparing arterials, and so on. After this, some of the attributes may be geographically dependent. For example, let's say there are some locations where there are more young population. There are some locations where there are more old population. So those are location specific kind of attributes. So first we need to figure out those tables, like out of the statewide data, to which we are trying to compare. So those discussion is provided here. This is a very important discussion here. Is very important. So for crash attributes such as manner of collision, crash severity, intersection related crashes, pretty much all the crash attributes, those are primarily influenced by roadway type and traffic volume. For crash attributes, similar condition would include all roadways with the same roadway type, which is the functional class: interstate, state highway, farm to market road, arterial. This is the roadway type, and ADT. So if our corridor has, let's say our corridor is an interstate corridor, and our corridor has I have an example here. So let's say we are analyzing a 4-lane freeway with an ADT of 1000 in an urban area. Then what we can do is we can look at crash attributes of all the urban freeways in the state, let's say state of Texas, with an ADT range of 80,000 to 120,000, kind of approximate range which lies around 100k. Then all the freeway in the state with the ADT range can be considered as similar conditions. So if we are trying to compare these tables, which comes from the crash data file, if we are trying to build these tables from crash data file attributes such as crash severity, intersection related crashes, manner of collision, weather may be a local thing, or alcohol related may be a local thing. So these two may be more related to geography, and these three are more related to roadway. And we have hundreds of different attributes to look at, so these are more related to roadway. So we can create this table by finding all similar roadways within the state which has this and these attributes. So whether the roadway lies in urban or rural area, and what is the functional class of that roadway. By finding out those corridor specific or project specific data, we can build a set of tables that belongs to the statewide roadways, but for the same functional class and same ADT range. So that's the first attribute. Second attribute is persons attribute, such as age, intoxication, seatbelt usage. These are more of a local thing. There are local or regional behavior are more of a regional behavior. Therefore, the personal attributes for a project can be compared against similar personal attribute within a county or district. So what we can do is we can look at the crash trend within a county and district, and we might use the same roadway class. And the last one we have is the vehicle attribute. A vehicle attribute such as vehicle make, model, vehicle type, vehicle defect can vary by both roadway type and region. So therefore engineering judgment should be used to define similar crash conditions for vehicle attribute, and this may change from project to project. So when we are trying to compare whether the heavy vehicle crashes for one project, then we might look at similar roadway type, or we might look at the heavy vehicle crashes within the region, or we might look heavy vehicle crashes within the region but for the similar roadway. So engineering judgments should be used to define the similar crash conditions for vehicle attribute using roadway type, which we use for the crash attributes typically, and local region, which we typically use for persons attribute, or both of them. So to recap, for crash attributes we are looking at similar roadways with similar functional class and similar ADT as our corridor project. For persons attribute we are looking at local region, which can be local county or district, local regions. And for vehicle attribute we are looking at both of them. With the advanced dashboards, the percentage distributions of hundreds of attributes can be analyzed and check if the crash type deviates significantly from the crash percentage under similar conditions. So the definition of similar conditions comes from here, here, and here. Additionally, the attributes can be crossed with each other to generate tens of thousands of new attributes. For example, angle crashes with serious injury is a crash attribute or crash type generated by crossing manner of collision and crash severity. So what we can also do is we can look at two different attributes. So here we have manner of collision, here we have a crash severity, and then we can look at each manner of collision for each individual crash severity, and we look at that percentage. So instead of using a table, we will have a matrix, and then we can compare this matrix with the similar statewide matrix. So the number of element of a matrix will be number of attributes here multiplied by number of attributes here. So typically we have over 100 attributes from the crash data, and if we cross them with each other, we will end up with tens of thousands of attributes we can look at. So this is a power of advanced dashboards, where we can look at so many attributes and deep dive deep into the crash data to figure out some interesting crash patterns. So advanced dashboard can be built using Python or DAX within Power BI, and it's not very difficult. I would encourage young engineers who are pretty good at programming or writing DAX functions. I think the next generation is better than what we are doing. So you can use the DAX functions, and if DAX function does not work, then Python to build all this comparison within the Power BI. So the feature of advanced dashboard are as follows. The advanced dashboard can analyze hundreds of attributes. The analysis is automated between the projects. So the good thing is, once we build this dashboard, we can just replace the data for different projects and all our analysis will be done. Advanced dashboard can heavily reduce the traditional descriptive analysis work, and it can actually enhance the traditional work. So we will look at one example of this dashboard through Power BI next. So advanced descriptive analysis is currently in development by different DOTs and researchers. However, engineers can set up their own advanced descriptive analysis dashboard. So the engineers can do their own in-depth analysis, and engineers can build the dashboard in a way that is more suitable for projects. So the state DOT dashboards are more focused on their vision, whereas as an engineer we can build our own advanced analysis dashboards which are more suitable for projects. So we'll look at one advanced kind of a comparison of the dashboards soon. Here we have a dashboard where the data on the left hand side is for the project, and data on the right hand side is the statewide data for 5 years. So there are about 3 million crashes in the state, and this is a corridor. Let's say our corridor is located in the rural area. Right now the data I have is both for rural and urban for our project. So let's say we want to figure out the rural crashes from the corridor and rural crashes in the statewide. So I have this master filter here, and if I click yes, the left hand side will filter out for the rural area and right hand side will filter out for rural area. And looking here, we can see that the fixed object crashes is 43%, whereas the statewide average is 40%. So we can try to draw some conclusions. Let's say rural frag is no, then we can look at some of the interesting ones. Let's say left turn crashes for the project is 16%, whereas the left turn crashes for the statewide is 11. So depending on how we are declaring high or low, left turn here is relatively higher than the statewide average. Also what we can do is, if our corridor has a particular roadway type, let's say our corridor is a farm to market road, so on the right hand side we can currently the right hand side is showing all the rural accidents, but we can filter it out by the roadway type. So that, let's say I'm selecting farm to market road. Now we can look at some distribution for farm to market road only. So assuming the left hand side corridor is farm to market road, if I select the farm to market road here, we'll notice the right hand side will get filtered. In this case, the fixed object crashes is 27%, which is higher than regular farm to market road crashes in the urban area. Let me switch this to rural. So in rural area, for our corridor, which is farm to market road, let's say we have 43% crashes, and for the same rural area here we have 44, which is kind of similar. So we can draw these kind of conclusions by comparing the statewide data and by declaring by bringing up these tables which are similar in nature to the corridor. So assuming that the corridor is farm to market road and in a rural area, we can create a table for the project which is for that particular functional class, and roadway type, and then we can compare. For the person attributes, we can do the exact same thing, but instead of using the highway system, we can use the locality. So let's say this lies in district, some district, let's say district 2. Then we can bring in the statewide data and select the district 2 to figure out all the crash pattern within district 2. So this is how with advanced dashboards we can have some more in-depth analysis. The right hand side can be built either using DAX function or Python, or either, or there can be many other things which Power BI allows us to build. Now the next thing would be to how we can summarize those results. So let's look at how we can summarize these results in a more easy to use format. So in previous video we saw what we had was, let's say this is a line, and on the top we have corridor tables, which is for our project, and we have similar facility tables. So we have, let's say, statewide, or we have for particular county tables. So we are comparing table 1 with table 1 here, table 2 with table 2. Now we know that there will be hundreds of tables. Let me draw them out just to show how much table and how much data we are playing with. So we have hundreds of tables here, and if I can change the color, and we are trying to compare it with the regional or the statewide tables, and we are trying to compare each line from table 1 to each line in table 2. So previously in the dashboard we can either do it visually, however we can write more DAX and programming functions such that we compare these tables. Let's say in this table we have some data here, some percentage here, we need to compare it with some percentage here. Then we can write a DAX function, or we can write a code such that these numbers are compared and the difference are calculated. So let's say this attribute is at 30% and this attribute is at 20%. So we can calculate the difference and declare some threshold such that if this difference exceeds a threshold, then this data will be there, otherwise this data will disappear. So what this can give us is the list of priority, or list of attributes and their components that are more critical. So let me take one table example, and so how we can summarize this one. So here we have corridor here, and here we have statewide. So let's say we have manner of collision here, we have angle, we have side swipe, we have head on, let's say we have left turn, we have rear end, and so on. Similarly for the statewide or the similar facility, we have angle, side swipe, head on, left turn, and rear end. So what we can do is we can compare the percentages using DAX function or some programming languages, and then we can try to see which attributes are the difference in which attributes are more significant. And we are mostly interested in attributes that are higher in corridor. So for example, let's say the rear end in both of them are similar, left turn are similar, but head-ons are similar, but side swipe crashes for the corridor is significantly higher than the side swipe crashes in the statewide data. So what we can do is we can write a script such that the head-on does not appear, left turn does not appear, rear end does not appear, angle does not appear, depending on the thresholds we are setting. So in the dashboard, what we will have is only the side swipe. So on the dashboard, we will be left with side swipe from table 1. Then we will have some other attributes from table 2. Table 3 might not have anything. So let's say this is table 1, table 2. Table 3 may not have any attribute that are significantly different. Then we have table 4. So we can reduce the numbers we have to look at by defining these percentages and kind of filtering out everything that is not relevant for this particular project. So in this project we can have table 1 with only side swipe because side swipe was significant. Let's say here we have alcohol related crashes, here we have travel direction as east being most significant. So we can reduce the presentation, and now all the attributes we are left with, these are the significant attributes which we need to look for the project. So this is how we can perform the advanced descriptive analysis by using the statewide data, then comparing the corridor or comparing our study area with a similar facility for a larger network, and then trying to figure out whether certain attributes deviate significantly from what is expected based on the larger data set. Once we figure out whether that attribute deviates significantly by predefining a threshold, let's say 5 to 10% is typical threshold we are looking for, then we will delete all the attributes that does not deviate significantly. So we will compare, let's say, hundreds of different attributes and the different elements of those attributes, and we will only keep the one which meets the criteria of being significantly different than the expected. So in this way we can kind of perform a better and more intuitive crash analysis. The good thing about Power BI dashboards is once it builds for one project, it's built for other projects too. So once we build it the first time, it's automatically built it for future projects. So for future projects we don't need to build anything, we can just replace the data and it will give us a set of factors that are more relevant for that particular project. So this is an advanced and very fast and kind of intuitive and better way of performing the descriptive crash analysis. So that's all we have for the crash analysis chapter. I hope it was helpful, and I'm hoping it will bring in some new ideas, and we can do some better crash analysis in the near term future. I'm sure a lot of this will get automated pretty soon, so we don't have to build all this thing again or even have the need to discuss this thing, because once this is built. In the next videos we will look at predictive safety analysis. That's another important topic. Predictive safety analysis are typically done with the guidance from highway safety manual. So we will look at predictive safety analysis in the next video. Thank you.